Hi everyone, great to be with you this afternoon. Physics paper tomorrow, physical science paper 1, and it's great to have Indy with us today.
Hi John.
Hi Indy, how are you doing?
Good, you're looking smashing.
Yeah, now the reason that we like this, and I've got my yellow Support South Africa shirt, and Indy's got her green shirt on, is we think you guys, class of 2011, are great. You're worth supporting. And that's why we are wearing our kit today.
No, we're wearing them for you.
Not for the cricket, not for the rugby players. No, it's for you guys. Class of 2011, we want to really get behind you. We know that you're going to do great. You're going to make us proud. We're into supporting you.
Yeah, we are definitely. Guys, we are so excited. We're especially excited for the session. I know, John, you have a lot of followers and people that love watching your show. I just want to let everyone know, please join in on Facebook. That's www.facebook.com/learnextra, and that's with an X, XTRA. Also, follow us at LearnExtra on Twitter.
Yeah.
And then also,
you can phone us.
Yeah.
Remember, you can phone us on that number 086 1058 262.
And I'll also put that number up on Facebook, because it would be nice to have a few people phoning in. Yeah.
Okay, now we've had a huge response to physics questions. I know that some of you are stressing, but guys, now's the time to relax. Just calm down. We're going to help you get through this. Now, the number one question everyone is asking is about work energy.
Yes.
So we're going to go through this really slowly. We've got a whole lot of people that have asked a section of questions, and it was Musa that sent us this question from Mpumalanga, which I think covers forces, things on an inclined plane, as well as a whole lot of other stuff. So let's go straight to that question, and you'll see it's Layla and Mapelo and Bongi, and we're going to try and get through this question, and let's have a look at it. So hold on to your horses and let's go. It tells us the following things. So as we're reading through a question, remember we need to underline the important information and take note of it. So it says a 30 kg block moves at constant velocity of 12 meters per second along a horizontal surface. So guys, that means that if it's constant velocity, the resultant force here is 0 newtons. Okay? It's moving at constant velocity. It's probably a frictionless surface. Remember that this applies to Newton's first law. It then says the block slides up a rough inclined plane, and the incline makes an angle of 15 degrees to the horizontal. The block experiences a constant frictional force of 450 newtons while moving up the incline. And here's the diagram. So there we go. Newton's first law, we know that if it's going at 12 meters per second there's no resultant force. It will be going at 12 meters per second until it gets to that point. Now, this question says calculate the distance x that the block moves up. So we want to work out that distance that it moves up before it comes to rest. Remember what rest means. Okay, rest is another word for saying stationary. It's another way of saying that the final velocity is 0. So I'm going to write that on the board to remind us that the final velocity here is 0 meters per second. Okay, so now this is a really nice question, and there are a whole lot of parts to it. So I want to break it down into its different parts, and by doing that, I'm going to see if I can help those other people who had other questions, not just, who was it? It was Musa. So we want to just try and answer some of the other questions as well. Now, the first question Layla asked is, guys, please help me with the work energy theorem. So I'm going to write down the work energy theorem as a formula. We say work net is equal to the change in kinetic energy. Now, you can write it as delta K, or you can write it in this form. Work net is equal to the change in kinetic energy, and you're going to write EK. And both of those are acceptable. You can use whichever one you've been taught. So this means that if I have an initial velocity, I can work out the kinetic energy. Remember, kinetic energy is half mv squared. And I can work out the final kinetic energy, subtract those, and I can work out the net work or total work done. Okay, so if we expand this formula, we're going to say it's the final kinetic energy minus the initial kinetic energy. Delta means change. Just want to remind you that the delta means change. And change, you always take final minus initial. And then what we're going to do is we're going to fill in the formula. We're going to say half mv final squared minus half mv initial squared. Okay, so this will give us the net work done. So let's just have a look at the question again, and I want to see where the initial and the final are. So if we just start not answering the question we're doing now, and we say, let's just make that point A and that point B, and we're going to say, what's the work done between those 2 points? Notice it has a constant velocity of 12 meters per second. That means that by the time it has a certain kinetic energy there, certain kinetic energy there. What's the difference in those kinetic energies going to be? Well, kinetic energy, change in kinetic energy, delta K, is going to be 0. And that makes absolute sense. Remember what we said earlier. We said the resultant force is 0. And you should also then remember that W net is also equal to F delta X times cos theta. And if F is 0, then what we know is that no work is going to be done. So both the formula give us no work, and that's really nice. Okay, so I'm now going to do from the bottom of the ramp to the top of the ramp, which is the question we were really interested in. So we were told that the final velocity was 0, so I'm going to substitute my values in. The mass was 30 kilograms. The final velocity is 0 squared minus half 30. The initial velocity was 12. And I'm going to square that. Okay? Now, just for speed, we could show that to you on the calculator, but I don't want to do that right now. I've worked this question out already, so I'm just going to go straight to the answer. You check me on the calculator, your calculator, but we've got so many questions, I want to try and cut down on time of just using the calculator. See if I've got it right. I got minus 2,160 joules. Okay, so I hope that's helped you. Just to recap what the work energy theorem's about. Work energy theorem tells us that the total or net work is equal to the change in kinetic energy of an object. Okay?
Fantastic.
I hope the guys have got that, because that's the easy part. That's the beginning part.
Yeah.
But there's a little bit more of a challenge to this question, so let's move on.
Let's move on.
Okay.
Cool,
so the next part of the question is we were asked to find distance x. Now, before we get to distance x, I want you to understand what the forces are that are going to be acting on this 30 kilogram block as it moves from this point up to that point. So I want to think about the forces. And now, when you're doing this, guys, even in your exam, what they'll probably do is have a question like this, and I'm just making it up because I wasn't given all the questions. They would probably ask you to draw a free body diagram. Now, I think it was one of the other people that's on this list here asked us about forces and free body diagrams and on the inclined plane, and there were a whole lot of other people that I haven't included. So I'm going to draw the free body diagram of this block as it's moving on the plane. Okay? Remember, free body diagram, you put a dot to represent the object. Now, what's the next thing you're going to do? You're going to indicate all the forces acting on it. And what I'm going to do is I'm just going to draw in a dotted line here for you. You don't have to do this in the exam. Okay, in fact, I'd suggest you don't. But just so that you can see that that's the plane of the inclined plane. And we've got the box drawn over there. And we're now going to draw in the forces. What are the forces acting on this? Well, the force that always acts downwards is the force of gravity. Just as an aside, somebody was asking about the force of attraction between the moon and the sun and so on. It's related to this. It's the force of gravity. Remember, any two objects that have mass in the universe, they're going to attract each other with the force of gravity. Newton's universal law of gravitation. Okay, let's move on to that. the second force. Now, if you draw a free body diagram, make sure you draw the force with a ruler. I didn't draw it with a ruler here. And you label it. But you must say what it is. Fg is the force of the Earth on the box. So something like that. The second thing you're going to do is you're going to say, but hold on, guys, we've got a normal force. A force of the surface. It always acts at 90 degrees. And we put it Fn. We're going to say Fn is the force of the surface on the box. And now, what's the other force that we've got? Well, we were told that there is another force, and it's the force of friction. And it's acting, the object is moving up. So remember what friction does. The motion is up, so that's the velocity. We know it's decreasing. The frictional force always acts in the opposite direction to the direction of velocity. So that's frictional force there. So what we do is we'd write Ff, this is frictional force, the force of friction. And because we were given it in the question, we could even actually fill it in, go back to the top there, and you'll see 450 newtons. So if I wanted to, I could even write in here equals 450 newtons. And it's going to be down the slope. Okay. Whereas the velocity is up the slope. So that would be a free body diagram. Now, just to make sure, you don't have to include the velocity. So that would be your free body diagram drawn like that, and we've got it very clearly written out as well. Now, some of you might be looking at that and saying, yeah, I understand that, but it doesn't give me the whole picture of what's actually acting on the block. And here what we've got to do is we've got to look at components. And I know some of you are raising your hands and say, please, not components. Oh, no, components are terrible. Components are your friends. Make friends with them now. Okay? So what I want to do is I want to show you what we're going to do. We're going to break this force due to gravity into two components. And then you will be able to see a different free body diagram, which I'm not going to draw in as much detail. So what I'm going to do is I'm going to say to you, guys, here's your slope. You can draw that same diagram. There's the box. What we're going to say is we know that we've got the force of friction that's acting downwards. We know that we've got the normal force that acts at 90 degrees. Okay? That's the normal force. What we're going to do is we're going to break the force that normally goes straight down into two parts. Into a part that goes exactly equal to the normal force, and we call that the component Fg perpendicular. We say it's the component of the weight or the force of gravity perpendicular at 90 degrees to the slope. And then what's the other one? We can't just have one component, we've got to have another component. Now, which way is gravity pulling? Well, gravity always sucks. It pulls downwards. So we recognize that that one was Ff, but the force of gravity, the component of gravity parallel to the slope, can be drawn in over here, and I want to draw it in pink so you can see that it's going to be like that. That's going to be Fg parallel to the slope. So it's Fg parallel, it's the component of Fg, but it's parallel to the slope. Okay, so there are two ways of drawing free body diagrams. Number one, that way, which gives you all the forces. This one, number two, gives you the components. Okay, now what I suggest that we do is we always try and look at the components so we can see what's really going on. Because it's critical in this section of work that you understand the idea of the word resultant force. And what I would like you to do, we're going to go to an ad break in a few seconds. What I would like you to do is to take a careful look at that diagram again with the components and draw for me, while we're in ad break, draw for me what the resultant will be. How are you going to put these together to show me the resultant? Okay, that's a little challenge question. I think that. Do you think the learners will be up to it?
I think they will. I have complete faith in them.
Okay, if you got the answer, you have an idea of what it is, maybe even tweet us or put it on
Facebook at Learn Extra on Twitter. Don't forget facebook.com/learnextra. We are here. We are listening. We are keen. We want to know your answers.
Okay, guys, let's go to an ad break and we'll see you straight after that.
See you now.